So, ladies and gentlemen, it's 4 o'clock. I'm very glad to welcome you at this special open session, which is organized in frame of the International Conference on Research and Applications of Plasma 2023. The conference is organized by the Institute of Plasma Physics and Laser Microfusion. So first, please let me introduce the director of the Institute, Professor Andrzej Gałkowski. The session is open for audience, registered person, and also for the people who join us remotely and watch us on the YouTube. So thank you to be with us. I'm very glad that also press decided to join this special session, so welcome. We decided to organize this special open session because after the announcement of the records achieved both in the magnetic confinement fusion and also laser fusion, we observed very great and biggest interest in Poland in these areas, and we received many requests for comments, for interviews, for lecturers. So that's why we decided to organize this as a part of our conference. And for this reason, we invite experts from the big laboratories who participated in this, who were a part of the team which achieved the records in fusion, and they are experts in physics and plasma and fusion. So I think we can start the official part. And please first, I have a pleasure to introduce you Dr. Ernesto Lerche from the Belgium Royal Military School, who will give us a talk on the magnetic confinement fusion record achieved at JET by the European research community. So please, Ernesto, the floor is yours.
Thank you very much, Monica, and welcome everybody. I hope that in the next 45 minutes, I'm going to convince you that we are a little bit closer to achieve to realize DT fusion on Earth. And I'm going to give you an overview on the high performance DT experiments that we have been doing in JET back in 2021. My name is Ernesto Lerche from the Plasma Physics Laboratory in Brussels. But in the last 10 years, I've been seconded in the Culham Science Center in United Kingdom, where the JET tokamak is actually installed. As you can imagine, I'm speaking on behalf of a lot of scientists that have contributed to these achievements, and we refer to them as the JET contributors, and a comprehensive list of all these researchers is given in this paper by Dr. Mayu of 2022. So this is just to give you an idea of some of the laboratories that are involved in this project, and you can easily recognize our host of this afternoon here, the Institute for Plasma Physics and Laser Microfusion. And here in the bottom, you see the symbol of the Eurofusion Consortium, which is the European consortium that actually coordinates the magnetic fusion efforts in Europe. So establishes the priorities and coordinates the efforts of all these laboratories and all these people together. So let's start with the very basics. You all know probably that there are two nuclear power sources that we can realize here on Earth, namely nuclear fission, which consists on splitting a heavy atom into two lighter atoms and harvest the energy that is released in this process. And we have the nuclear fusion, which is pretty much the opposite, where we take two light atoms, we fuse them together, and we also manage to release some energy in this process. If we go a little bit more in detail, on the left panel here, you can see a typical nuclear fission reaction where a neutron is bombarding a heavy uranium-235, creating two other heavy atoms of barium and krypton here, releasing a huge amount of energy. And this process also releases a few neutrons, 2 mega-electron-volt neutrons. Some of these neutrons are reused in the chain reaction process, so they are reused to fission again some of the heavier ions or products, whereas some of them are then used to extract the energy from this process. But there are a few caveats on this nuclear fission reaction. One of them is that these neutrons that are ejected, they are at too high energies for the optimal cross-section of those reactions. So we need moderating bars to slow them down and to control and optimize the chain reaction rate in general. Obviously, as shown here in red, you have a strong gamma radiation, which is dangerous to life. And as all of you know, I'm sure, that there is long-lasting radioactive waste that can last thousands of years. On the right panel, you see a more detailed example of a typical deuterium-tritium fusion reaction, where we take light atoms of mass 2 and 3, they fuse, they produce a fast 3.5 megaelectron volt helium particle, which we call an alpha particle, and they produce a 14.1 MeV neutron. And this neutron is then directly used to extract the energy of this process. So one thing is that this alpha particle is directly used to reheat or to self-heat the plasma via collisions with deuterium and tritium ions. So this is absorbed inside the whole process. And once this energy gets large enough, or once you have sufficient alpha particles to keep things going, we call this situation a break-even. And it's not that there is no radioactive waste at all. There is no long radioactive waste, but there is a little bit of activation of some of the internal machine components due to the neutrons. But, you know, at most, this lasts something like tens of years. And finally, just a few words on the power generation efficiency of these two processes. So you see here on the left-hand side that 1 kilogram of uranium-235 is equivalent of 2.7 thousand tons of fossil fuel. So this is already an impressive number, I'm sure you reckon. And uranium needs mining and enrichment to be appropriate for nuclear fission plants. On the fusion side, we see that 1 kilogram of deuterium-tritium fuel is actually even more efficient. It's equivalent of to 10,000 kilograms, 10,000 tons of fossil fuel. And basically, deuterium is easily extracted from seawater. Tritium still needs some breeding from lithium, but it's not really a big deal either. So let us talk a little bit about the possible nuclear reactions that we can realize here. On the left panel, you see here what we call the cross-section or the reaction probability as function of the energy of the particles that are going to fuse. And you have different fusion reactions depicted here in this figure. And clearly, the one that is most interesting for us is the red curve here, this deuterium-tritium reaction, because first, its maximum, or it can be realized at the lowest energies of all these reactions depicted here, and it has the highest probability or the highest cross-section of all the other examples shown in this picture. Still, you need to get here at the very top of this nuclear of the cross-section, you still need something like 30 to 40 kilo electron volts of energies, which corresponds to hundreds of millions of degrees Celsius. So it really requires a hot plasma to reach these kinds of temperatures. But also would like to notice, and this is not usually mentioned, that this is an intrinsically safe reaction when it comes, for example, to a reactor. Because as you noticed, it has a maximum, it's not monotonic. So when your particles start to be too energetic, you already start going down into this red curve, and the probability for a reaction to occur decreases. So you typically want to stay here around this maximum here. Here you see an example where we are for jets. This is more or less the region where we operate, around 15 kilo electron volt of energy, so about 10 kilo electron volt of temperatures. For the bulk ions, about 100 kilo electron volts for the injected fast ions, and I'll come back to that. So that the nuclear reactions in a machine like JET, they are basically split into two branches, if you want. One we call the thermonuclear branch, which is really due to the fusion reactions between the thermal bulk plasma ions. And the other branch is what we call the beam particle reactions, which is the nuclear reactions that happen when a fast ion of the order of 100 kilo electron volt collides with the bulk target plasma. In the future reactor like ITER or other machines, thermonuclear reactions will be dominant, and these beam target reactions are really negligible, but not in the case of JET, and I'll come back to that. Just a very few words what we need to achieve fusion, and this is then expressed here by the so-called Lawson criterion for fusion, which gives the figure of merit that to achieve fusion or to achieve to be able to extract energy from a fusion reactor, you need the product of the plasma density, the plasma temperature or the ion temperature, and what we call the confinement time, which is the ratio between the internal energy of the plasma and the power you put into the plasma to get into this energy, to be higher than a certain number. And there are two definitions here. I mean, this is very broad because it depends a lot from which kind of machines or which kind of things we are talking about. But these two concepts are pretty universal. There is what we call a break-even, where the fusion gain is one. So the fusion that you produce internally in your machine is the same as what you need to put in. So in some senses, the losses are compensated by the alpha heating produced. And so your triple product has to be larger than a certain number to achieve that. And it has to be even larger if you want to exploit such a machine as a commercial reactor, where you need to be in a condition which we call ignition, where this fusion gain theoretically goes to infinity, because what we want to achieve is that the alpha heating alone is enough to sustain the plasma at these very high temperatures, and in principle you can switch off the input power. In reality, it's never like that. You also always have to keep some power there to maintain the plasma and to continue the processes. And just as an introduction, so we are going to be talking about magnetic fusion in this talk here, which exploits large temperatures in this triple product and relatively large confinement times. So we could envisage creating a quasi-steady state fusion reactor using this technique. And the next talk by Dr. Trosseille from the National Ignition Facility is going to show you the other possibility to realize nuclear fusion on Earth, which is called the inertial confinement fusion, which basically tries to maximize the density in this triple product. It has a pretty low confinement time of the orders of say, picoseconds or so. So it's more appropriate to envisage something like a post-reactor based on this technique. Good. So magnetic fusion. What I guess many of you are not familiar with what a tokamak is, so I have to go through this very quickly. So a tokamak is such a toroidal device which we use to confine and to create this very, very hot plasma without letting it touch the walls. And this is a sketch of a tokamak here. The main features are these blue magnetic field coils here. These you drive currents through them and they will excite a very strong magnetic field in that direction. The example here is this blue arrow, and this is of a few Tesla. So it's, if you compare with a standard MRI equipment, it's a few times higher than this equipment. And the second ingredient is this central solenoid here, which will induce ohmically a plasma current in the same direction or opposite direction, it doesn't matter, or in this toroidal direction here. So also shown here. And this current creates itself a magnetic field in that direction shown, so a poloidal magnetic field, so that the resulting magnetic field is something like a helical structure around the torus here. So it's a combination of these two fields. And by Lorentz force, the charged particles that exist inside this plasma, they are bound to these magnetic field lines, so they execute what we call a gyro motion, so they are magnetically confined around these magnetic field lines, and they almost don't touch the wall, so that you can sustain such a 1,000,000 degree plasma without melting any plasma-facing components. This is the example, an example of the jet tokamak in Culham, United Kingdom. So here you see on the left-hand side a sketch of the tokamak with an average person standing close to it. It's capable of a magnetic field of something of 3 to 4 Tesla typically, and we do plasmas with currents of the order of a few megaampere. And this is a cross-section of the plasma that is created here inside this vacuum chamber. You see the dimensions. It's roughly 1.5 meter wide by 2.5 meter high, giving you a plasma volume of the order of 80 cubic meters. And I would like to call your attention to the different colors here. So this red one, red colors, is what we call the core of the plasma. These are closed magnetic field lines. The particles are really confined here, and they stay here, and they hopefully undergo fusion. And then there is these open field lines here, the blue lines, which we call the scrape-off layer. So the particles that are constantly being drifted outwards in the radial direction, they eventually meet these magnetic field lines, and then they follow them and they are exhausted, or they hit these divertor targets here in the bottom, which is the main exhaust of particle energy. So most of the power that we put in partly is radiated away, but the other part is really absorbed by this structure here on the bottom of the machine, which we call a divertor. This is now a real picture of jets, so that you can see a little bit the complexity of the machine with all the heating systems and all the diagnostics and all the cables and everything. Again, call your attention to two real people here on the bottom. So this is a huge piece of equipment, very complicated, requires a big team of specialists to keep it going. So you can imagine if something goes wrong in a small cable here, you really need to know which cable you need to change, and a few people only do. Another interesting feature of jets is that up to the 90s, most of the tokamaks in the world, where they had internal carbon-based plasma-facing components, either the walls or the divertors. But carbon is not compatible with fusion reactions by many reasons, in particular because it retains a lot of tritium, it erodes very easily. So back in 2007, JET was equipped with what we call an ether-like wall, which had a beryllium wall, here represented in green, and it has a tungsten diverter. And remember why tungsten? Because this is really the part of the machine that takes the heavy load of particles and of heat loads. So beryllium, having a fusion temperature of about 1200 degrees, would not be appropriate for this part of the machine here. But for the wall, it's okay, because it's, I mean, there are heat loads on the wall, but they are much less severe than the ones that hit the diverter. And finally, to put things in perspective here, the next generation device that we will have in Europe is so-called the ITER reactor. And here you can see a difference in size between JET, which we already have the impression that it's a very big machine, and this is in scale, how ITER will be. Here again, you see an average person. The volume will be 10 times higher, so this already says it all. We will have 800 cubic meters of plasma being created here with a high magnetic field, much higher current than JET. It's something really impressive. It's, of course, a €1 billion project, and it's a consortium of many countries that are involved in that. One of the main differences between these two machines, aside from the size and the complexity, etc., is that the magnetic field in JET is created by copper coils, and also most of the equipment inside of the machine is not actively cooled. So the pulses are really limited in duration to something like 10 to 20 seconds because of these ohmic limitations and because of the heat load limitations. ITER, of course, will not have these limitations, because the magnetic field and all the structures will really be superconducting coils, and everything that is exposed inside the plasma will have active cooling. So we expect really long pulses there, things of the order of 10 minutes or so. That is the wrong direction, I think. That is the right direction. So now we come to the actual outline of the talk after this introduction. So I'm going to show you briefly what were the fusion power levels that we achieved in the last JET D2 campaign in 2022. Unavoidably, I will have to give an introduction of what we call the high confinement mode of plasmas and the consequences of it. Quickly show you which kind of auxiliary heating systems we use to heat the plasmas to these temperatures that they manage, that we manage to measure fusion reactions on them. I mainly spend a bit more of time showing how you can develop different plasma scenarios with higher currents, higher fields, more density, less density, etc., and which have been the best performing ones in the latest campaign. Finally, a few words on what we learned about isotope effects, and by this I mean what happens when you take a plasma that is initially hydrogen with a mass 1, go to a deuterium, which is a bit heavier, mass 2, finally go to a tritium, and culminate in a DT plasma. So I will just go very briefly of what happens with the plasma core on these situations, and similarly what happens with the plasma wall interactions and sources due to isotope effects, because this is very important, really. This is one of the crucial matters for a fusion reactor. And also because the Polish Association has is a specialist in this area here, so I'm sure you will be very interested in all that. Let's start with the main goals of this deuterium-tritium campaign. So the first one, and this is the one that is probably the most exciting perhaps for this audience, is to demonstrate the high fusion power, so 10 megawatts of fusion sustained for 5 seconds. Another which is very important is to demonstrate integrated radiative scenarios in the conditions relevant for ITER, and I will show you what this means. This basically means creating plasmas that can relieve a little bit of these heat loads from the diverters so that you can have a longer pulse without having too much heat loads, and this is very important for fusion reactors. Of course, there have been a lot of works trying to demonstrate clear alpha particle effects. This is something that people have been trying for many years to pinpoint what is the kind of alpha heating and how you can identify it. I will not have time to go through that, but I refer to these 2 papers here that are very interesting. This was demonstrated, it's just that we don't have time for that. Then, as mentioned, to clarify isotope effects on energy and particle transport, so we quickly go through that, and address the key plasma ball interaction studies. And if there is time, which I probably think there won't be time, I would like to say a little bit about radio frequency heating schemes that are relevant to ITER, because this is actually my specialty. But we will see. So, what happened in the past? It's mainly 25 years now since the last deuterium-tritium experiments ever done on Earth. Aside from an exploratory campaign in '91 in JET, so here on the right-hand side, there is the fusion power as function of the duration of the plasma discharge. So you see here in black, these were some exploratory pulses done in '91 in JET. But the most interesting ones are the ones in green here. This is a deuterium-tritium campaign done in a tokamak called TFTR in Princeton back in '94, '96. And you see that transiently this achieves something like 10 megawatts of fusion power. And then there was the first DT campaign in JET in '97, which you see examples of the pulses here. We reached up to 16 megawatts of power transiently in what's so-called the hot ion mode, but it doesn't survive very long. But we also achieved relatively stationary pulses here of 4.5 seconds with an average fusion power of 4 megawatts. Not only DT fusion products were measured, so proving that we can realize DT fusion in a machine or in a magnetic confinement machine, but also at the time already, some of the plasma physics effects linked to these isotope effects, so to heavier ions, were also identified, and this is why one of the main topics of interest nowadays. So just to remind you, the emphasis of the new experiments in JET, they were not on getting peak performance like these pulses that I'm showing here, but rather to try to take a sustained performance here and bring this level here up to the level of 10 megawatts. So these are already some of the main results that have been achieved. So these are the best stationary pulses that have been recently achieved. So these are the world records on fusion power and energy ever achieved in tokamak, and they were achieved in DT2. In red, I give you an example of what we call a tritium-rich plasma, which reaches, so here in black you see the target, the 10 megawatts for 5 seconds, and this was reached. We achieved actually 10.1 megawatts for 5 seconds in average here, with a total energy of almost 60 megajoules, so this is really impressive. And although JET was not designed really to have a fusion gain, an important fusion gain, it's worthwhile mentioning these numbers. So if you take the average fusion power here and divide by the 33 megawatts that were needed to achieve these plasmas, we get something like a number of 0.3 here. In blue, we have another example of a 50 DT plasma in blue, a little bit less performing, and I'm going to show you why, actually. But again, it's nicely sustained for 5 seconds. It gives an average of something like 7.5 megawatts for 5 seconds, and of course, a lower fusion gain by definition. And just as a comparison, in gray here is the old results obtained with the carbon wall, with the JET DT plasma at the time. And just a quick remark, these oscillations that you see here in these fusion curves here, they are mainly due to the oscillations of the auxiliary input power. And I will come back to you. Sometimes the power fails and then it recovers, etc. The reliability is not 100%. And these are another pair of examples for the highest fusion power. They were not maintained for 5 seconds, but they exceeded 10 megawatts. So you see again, we have a tritium-rich plasma here, which reaches or exceeds 12 megawatts for something like 2 seconds here. And we have again a 50-50 DT plasma, which keeps around 10 megawatts here for also something like 2 seconds. And then suddenly you can see that the performance starts dropping. And this is due to the infamous core impurity accumulation. And I'm going to spend a few slides on that because I think this is important. But this has to do with the fact that now we have additional tungsten sources. You can imagine that if you put a lot of heat loads in the diverter, that part of this tungsten is sputtered away and can make its way to the core of the plasma. And if this happens, sometimes you can never recover. Introduction to what is a high confinement regime. So in tokamaks, we basically have what we call the L mode. So it's the standard classical low confinement regime. And we have what we call an H mode, which is a regime that you can reach with an improved confinement of particles and energy. And to get there, what you need is a certain amount of power. And Dr. Solano already told you something about that on Monday. I'm going to show a slide of hers. But what happens is that once you go through this threshold and the plasma comes into this very convenient states, you create what we call an edge transport barrier, and I will not go into the details here, but you simply lift up all this part of the plasma here at the edge, which we call the pedestal, and then all the particles and energy are better confined here in what we call the core. Basically, all high-performance plasmas nowadays, they are in this so-called H-mode regime. But nothing comes for free. So when you reach this H-mode regime, you have some instabilities here in the plasma edge, which are called the edge localized modes. And I'm going to spend 1 or 2 slides on them because they are really important for the plasma. So as mentioned, the ELMs or edge localized modes, they are due to an image instability that occurs in the plasma edge that periodically exposes particles and energy from the plasma core here, laser core, to the scrape of layers, to these open magnetic surfaces here. And here you see a typical signature. Once you apply the power, you get into the so-called high confinement regime, the H mode, and then you see, for example, in the beryllium emission, these very, very periodic spikes which correspond to expulsion of particle and energy from the core. And this is a beautiful picture, not from JET, unfortunately, because we don't have such sophisticated cameras there, but from the MAS tokamak, also in the United Kingdom, which shows you a structure of these ELMs, this filamentary structure at the plasma edge, which is one of the typical signatures of these edge localized modes. And why are they so important? Because they play a key role in the plasma performance and stationarity. If the ELMs are too slow, you don't have efficient expulsion of particles and energy from the core, which help you controlling the impurities. So you may end up with a high radiation in the plasma core. If they are too fast, they degrade your pedestal and your core performance, and you come closer to what was the L mode, and you degrade a little bit your H mode. And this is also illustrated by this experimental data here. This is the neutrons detected in similar discharges as function of the ELM frequency, and here you see, when you go too low in the ELM frequencies, you start having radiation and your neutrons drop down. When you go too fast in ELMs, the pedestal starts degrading and you also come down. So for a particular plasma scenario, it's very important to find the optimal ELM frequency to make it work right. That's why it's so important to control the ELMs, to have a stable and good performing plasma in tokamaks. Well, I don't like this slide, but I have to briefly go through that just to give you a flavor of what is coming next. But basically, there are scaling laws which take a lot of tokamaks, and people try to fit these exponentials of the main engineering quantities towards the experimental measured confinement times. And what you basically see here is that in a nutshell, that the confinement time, the energy confinement time, basically depends on the plasma current. So the higher the plasma current, the better. Depends on the machine size. That's why ITER is much bigger than JET. So you see here the plasma volume, basically. But from this scaling law, at least, which is one of the many proposed, it doesn't depend too much on the ion mass. What depends on the ion mass, and I'm going to come back to that, is the power that is necessary to reach these conditions of H mode where this scaling law was taken for. But the confinement itself doesn't seem to, from the scaling law, to depend, which is probably also wrong. But we'll see this later. Quickly browsing to the auxiliary heating systems. So this is a tokamak again, a sketch. So there are several ways of heating these plasmas to fusion relevant temperatures. You can use waves, either at a relatively low frequency, which we call the ion cyclotron heating here, tens of megahertz in a typical jet case. You can also inject waves at much higher frequencies, will then resonate with the electrons, which is what we call the electron cyclotron heating. And what is the main the main power in jet is injected by what we call the neutral beam injection, where you inject neutral particles with energies of the order 100, 120 keV, and they will collide with the ions and heat them up. Actually, all these techniques are based on heating a fraction of the particles, which then by Coulomb collisions will transfer their energy to the plasma and heat it up to the temperatures that we're interested in. And there's something important here. I know that most of you don't like equations, and I understand that. But this is an important expression that we have to chew a little bit. Coulomb collisions depends very much on the critical energy. And what is the critical energy? The critical energy is something that depends on the plasma temperature, the mass of the fast ion that is injected or that is heated by waves inside the plasma, and basically the plasma composition masses and charges. In jet, this critical energy is of the order of 200 kiloelectron volt. And what happens if you have a fast particle in the plasma that has the same energy as this critical energy? The probability that it will collide with an electron or with an ion, or that it will transfer its energy to an ion or an electron, is roughly half-half. If your ion is slower than the critical energy, it will mostly transfer its energy or its power to the bulk ions, deuterium and tritium, for example. And if the ions are very energetic, they would prefer to collide with the electrons and pass the power to the lighter particles as electrons. And this is very important because in jet, I'll come back to that. So here you see now the neutral beam injection in jet. This is, again, a typical sketch of such an equipment. It's very complicated. You have different injectors here, and you have to, well, it's a very complicated piece of engineering. This is a top view that shows the injectors. We have 16 megawatts of neutral beam injected on one side, 16 megawatts on the other side. Both of them, they go in the direction of the plasma current from this top view here. So they not only generate heating, but they will also generate rotation, you can imagine, because you are injecting momentum into the plasma, you are driving it. You can inject hydrogen, deuterium, tritium. As I said, we have a total of 32 megawatts of available power, but important is that in jet, the energy of these ions is of the order of 100 and 120 kiloelectron volts. So this is below the typical critical energy that we have in H modes in jet, meaning that these injected ions, they will mainly provide you, at least in the plasma core, with ion heating and not electron heating. And also, but this is just a coincidence, well, not a coincidence, actually it was designed like that, but if you remember the fusion cross-section there, these ions are also injected in an optimal energy range for the DT fusion cross-section. That's why in jet we have a significant part of the fusion reactions that come from this beam target branch, even if the number of ions injected is relatively small compared to the bulk density. And here on the left, you see a typical power deposition, radial power deposition profile of the beam ions in jet. So this is the power density, this is the radial coordinate, magnetic axis here, this is the separatrice. And as mentioned, in jet, from the total power in black here that you inject, most of it is transferred by collisions to the deuterium tritium ions because of the fact that we are below the critical energy. And just a little bit stays here on the electrons, and it's much flatter, much less peaked. The other system that we use in JET to create fast particles or to heat the plasma is the so-called ion cyclotron heating scheme, ICRH. And here you see these typical antennas that they launch fast waves into the plasma that are propagating here towards the plasma center. You see these are relatively long wavelengths of the order of 20, 30 centimeters in this case. Once they reach a layer for which the frequency of the injected wave is equals to the frequency of the gyro motion of a certain ion that you have chosen to heat, these waves are absorbed in a very narrow layer. And typically there are two possibilities. Either you inject a minority species like a hydrogen or a helium-3 or something, you drive a wave that will resonate with this species here, you will create fast particles, they will collide with the plasma and heat the plasma. But you can also directly heat the fuel ions with these waves. So you directly heat deuterium or tritium, which of course not only gives you efficient heating, but will also enhance a little bit the fusion reactions because you drive some of the particles to higher energies of the order, you create what we call a fast ion tail, which can also privilege nuclear reactions. And this is again showing again the collisional process. This is a typical absorption of the wave here of the ion cyclotron wave with a hydrogen minority. You see hydrogen takes most of the power. In this case, because hydrogen has a low mass, these ions will have an energy that is faster than the critical energy, and they will transfer a good bunch of their energy or of their power to the electrons and something to the ions. If you would do exactly the same exercise with a helium-3 ion, which has a 3 times higher mass and therefore a 3 times higher critical energy, these ions that absorb most of the RF power, of the wave power here, they will be still below the critical energy, and then they would slow down or they will transfer the energy by collisions to mainly the bulk ions. So this is more interesting for fusion than that. But there are other advantages of heating electrons. And this is just a few words comparing the two plots of the NBI and ICRH depositions, just to show you that even if ICRH typically has much less power than NBI, let's say a factor of 6 here, because these waves are absorbed in such a localized region inside the plasma, the power densities that you reach here in the very core are still comparable, even if the total power is very different. So you can expect that wave heating, not only ICRH, ECRH as well, but that localized wave heating has a stronger impact on the core plasma temperatures than something that deposits the power very broadly like the neutral beams. So let's go to the scenarios. There are basically two streams of scenarios that we have been using in JET. One is the so-called baseline scenario, and the other is the so-called hybrid family of scenarios. These baseline scenarios, they exploit the confinement at high plasma current. So you remember the Skeeny law showed you that the higher the plasma current, the higher confinement time. So this is what they try to do in the baseline. Go to high densities, which gives you at the end a medium core collisionality, not very low. So the beams don't penetrate so well. They still penetrate, but it's a much wider absorption. And you end up with a very dense plasma so that your ion temperatures and electron temperatures, they are pretty close because of very intense collisions, which we call equipartition. And this uses gas plus externally injected pellets to keep the ERMs going at the right frequency that you want them. The hybrid scenario, on the other hand, is lower plasma current in general. It's also lower density, therefore giving you lower collisionality. So you can imagine that the neutral beams, they penetrate much better and they give a much more peak deposition, similar to the one I just showed you 2 slides ago. And in these conditions, you manage to have the decoupling between ion and electrons because the collisions are not so efficient. So you manage to get plasmas where the ion temperature is much higher or is higher than the electron temperature. And normally we control the ERMs only with gas. Here we don't need the pellets for that. So let me give you an overview now of a real baseline scenario. You can see here the neutral beam curve, the ICRH curve. So these are the input powers. This is the bulk radiation. This is the signature of the ERMs measured by beryllium line in the diverter. Stored energy, here the fusion power, and here electron in red and ion in blue central temperatures. And as mentioned, you enter very nicely into H mode here. The ERMs are very well controlled with pellets. You have a relatively slow evolution because it's very collisional. So you really see it takes you 2 seconds to really get the maximum energy and the maximum fusion power, so of the order of 8 point something megawatts here. And as I had already told you before, the electron and ion temperatures, they are very similar because of the high cohesionality. Unfortunately, many of these pulses, these baseline pulses in jet, they suffered from this gradual radiation increase. At some point, the pellets are not able to control your ERMs anymore. You lose this impurity flushing, and you end up running away, and you are cut short, and you cannot extend the plasma. And there was not really enough time with full neutral beam power and full pellet operation to really optimize this scenario in DT2, unfortunately. This is just to show you that we are really confident in the kind of modeling, state-of-the-art modeling that has been done. So in these yellow stars here show you how the 1 second average fusion power values as function of the total input power. And then you have different modelings showing here. In particular, this blue here is the one that really mimics the experiments, and you really using the same conditions, 3.5 megaamp, 3.3 Tesla, and you really see that the agreement is fantastic. So this is very good news. This is a variant of the baseline scenario, which 5 minutes already. Okay, so this is a variant of the baseline scenario, just mentioning that we can use seeding actually to reduce we can use seeding to reduce the heat loads in the diverters. So these are similar pulses, and here you just see that you suddenly can reduce this. This is an example of a hybrid scenario now, and as I told you very quickly, this is this example is much more stable. Here you see the ERMs throughout. Stored energy is not so high as in the baseline, but it's pretty steady. And you see you have a constant fusion power, again, of the order of 8 megawatts here. And as I mentioned to you, the ion temperature is much higher, or is higher than the electron temperature, because of this less frequent collisions that happen in the plasma. I will have to be a bit faster here because I want to show you something on impurities, because I know that you are interested in that. So this is an example of a tritium-rich scenario, which is very similar to the previous one. And basically, you just see that everything is pretty steady here. And this is the pulse that actually reached the 10 megawatts for 5 seconds and gives you this 60 megajoule. And you see how much higher we have, something like 12 keV of ion temperature against 8 keV of electron temperature here. So the things are really decoupled in this example. Again, modeling shows very good agreement with the experiments, so we are very happy with all that. So I will not have time to show this. I already knew I wouldn't have time to show, but this is just to, I mean, there are, you can look into these references and understand that. But first, we saw that the energy confinement time, it was confirmed that it gets better when we go to deuterium and deuterium-tritium plasma, as you can see here from these pink and orange curves. And this is very good news for a DT reactor, of course. And as Dr. Solana showed you, also the power, and this is the power threshold needed to go into H mode as function of the plasma density, it's also reduced when you go from a deuterium plasma to a tritium plasma, and it's somewhere here in the middle when you go to a DT plasma. So these are all key information for ITER, and which are very promising as far as nuclear reactor is concerned. Quickly on plasma wall interactions. So as I mentioned, we have a beryllium wall, a tungsten diverter. Beryllium is mainly a problem because of wall temperature limitation and because it can create a bit more of tungsten sputtering, but it only creates radiation at the very edge. We are not worried with that. It's tungsten that we are worried about. There is no temperature limitation, but it is a problem if it comes to the core because it radiates a lot and you may lose your performance of the plasma. This is just to show that it was confirmed that indeed that the tungsten sputtering gets worse when you get to a heavier plasma mass or to a higher effective plasma mass. So from hydrogen to deuterium, this is the sputtering yield here. You see that it gets much worse, and then it only gets a little bit worse when you get to tritium. DT is somewhere in the middle, and this follows pretty much the theoretical sputtering curves here on the left. So everything is roughly well understood here, and everything is well in tolerance for ITER. Also, mid-Z impurities can be a problem, as I mentioned. We typically associate them due to the radio frequency fields created in the scrape-off layer. And this is an example by Agata Chomichevska, who is one of the hosts. And you see again that when you go from the hydrogen to deuterium to tritium, the radiation gets higher. In this particular case, this is mainly associated to nickel and beryllium, not to tungsten. But I really wanted to, again, thank the Polish Association for all the contributions they have been doing for the JET program, because, as I mentioned, some of the top specialists in impurity analysis are here in this room now, and thank you for that. Finally, the few words on core impurity accumulation, because this is one of the things that I told you was a disease of some of the plasmas, and this is a good example here. You see the input power, fusion power in green, radiation here in red. This is one of the bad examples, well, one of the good bad examples, a very illustrative one. You see that as time goes by, the radiation keeps increasing. Your central electron temperature starts decreasing, and this is because the impurities that were radiating here at the edge at 49 seconds, so here in this beginning here, were nicely here at the edge and everything was fine. They eventually and gradually make it to the core of the plasma, and when they radiate at the very plasma center, you see your plasma temperature collapses and hell breaks loose, the radiation goes high, you lose fusion, you lose everything. Of course, there is a counterexample where similar plasma, nothing of this happens. The radiation stays here at the edge until the end of the discharge. The fusion power is more or less constant, the radiation is more or less constant, and you see that the electron temperature you get here at the end of your discharge hasn't changed too much. There are techniques to control these impurities at the edge, but I was not expecting to discuss them. You need a very hot pedestal because strong gradients here at the edge, they keep your impurities out. Or you can do the opposite. Once your impurities are in the mantle already, you can apply localized heating in the plasma core. And this is an example. You see in the red case here, you have applied 5 megawatts of ion cyclotron heating in the core. The temperature stays constant, density stays constant, radiation stays constant, and the impurities stay here in this mantle region. Oppositely, when you don't put enough heating in the core, the impurities make it to the core and you lose the power. So, I think I have to go to the conclusions. There we go then. I hope I convinced you then that we are closer now to realize DT fusion here on Earth via magnetic confinement. We have achieved a record of non-transient fusion in JET with a full metallic wall, namely 10 megawatts for 5 seconds, about 12.5 megawatts for 2 seconds, with a total energy of almost 60 megajoule. But maybe the most important results of this is not the values themselves, but is that most of the calculations and the state-of-the-art models that we have been using to before the experiments and after the experiments to interpret this data are in very good agreement. So this really increases our confidence that we can extrapolate the performance of ITER and fusion machines within a relatively good error bar, within a good level of confidence. I showed you that you have different routes or different plasma scenarios that you can exploit to get to the nice conditions for fusion. They are mainly developed in deuterium, and then they are used or carried over to deuterium tritium. Once the isotope effects have been investigated, modeled, and at least understood to a reasonably good level, it's not too difficult to take a scenario that you developed in a deuterium plasma and bring it to a DT plasma. There are subtleties, but you really need to know where to go. You need something to guide you through this process. And I think that I called your attention that in a full metallic wall, in particular with high Z materials, that, oops, sorry for that, that you need to be very careful with contamination of the plasma core due to plasma wall diverter interaction. And there are several techniques that are being looked at to try to mitigate or to avoid that, like using ERM control for flushing the impurities at the edge, heating the plasma at the center of the plasma to screen them in the pedestal, or use this, which I didn't have time to speak, but try to induce large gradients at the edge to not let the impurities in at first place. As we speak, there is another deuterium tritium campaign going on in JET. The objectives are not on fusion performance, but they are mainly looking at some key aspects or key physics studies for ITER, mainly, again, scenarios with neon seeding to relieve a little bit the diverter heat loads, to have a better power handling of the diverter. A lot of focus on ELM control and small ELMs and some of the heating scenarios for ITER. But unfortunately, JET will be decommissioned next year, and the next deuterium-tritium experiments in ITER will only take place in ITER, and you'll have to wait at least some 10 years to see these results. Thank you very much for your attention. And maybe just before we go to the questions, I would like just to remind you that although everything was very fast today, there will be a special edition of Nuclear Fusion, which details of all these and much many more results. And I call your attention to read some of the articles that interest you that will come out there.
Okay, thank you very much. So now I expect some time for a few questions. So please, you have time for this. Yeah, please.
You showed that during obtaining power, nuclear power, during 5 seconds, let's say, the delivered power is 35 megawatts, yes?
The power needed to sustain this plasma, yes? Something like that.
The question is, it is the total energy which is delivered means this 35 times 5 seconds, or it is larger energy?
No, it is 35 times 5 seconds, yes.
It means that outside of these 5 seconds, the system doesn't operate.
No, it does operate, it's true, but the big energy we are talking about here is the auxiliary input power used to heat the plasma. What is happening is that the system does not operate in the long term, but it will take a couple of seconds to bring down the plasma current and to bring down the magnetic field.
Yeah.
But this energy is peanuts compared to the 33 megawatts that we're talking about.
Okay.
But you're right, there is, I think I didn't show a full example here, but first we start ramping the magnetic field a few seconds earlier, and then we start ramping it down here. But this is not the biggest chunk of these 33 megawatts here.
Okay, thanks.
Okay, any other questions inside, please?
So you mentioned the confidence in modeling of the fusion power. Isn't this to some extent linked to the fact that some part of this power came from the beam target interactions? In other words, are you confident with, for example, predictions for ITER, where the power should come from the bulk plasma interactions?
That's a good question. As a matter of fact, what we have found out in all this modeling is that it's actually easier to predict fusion from thermonuclear reactions than from beam target, because the physics is simpler. So I don't see any problem there. Of course, I think what is really most important in the predictive modeling is not calculating the fusion once you know the temperatures or once you know more or less what is there is easy. I think the difficult part is to properly predict the temperature and the density of the plasma with all the magnetodynamic effects, the turbulent effects, the transport effects that are there. But once you know what you will get, the fusion part is the easy part, because it's relatively, well, it's just a cross-section times the distribution function, so it's not difficult.
Okay, thank you. Is there any other? Yeah. Wait for the microphone, please.
You mentioned that you developed the impurity control methods. So how reliable they are? I mean, for ITER, we will need to control the plasma not for the few seconds, but like hundreds of seconds. Do you think it would be a big problem to use the same methods to prevent the some radiative collapse on the plasma in ITER? Can you like extrapolate it to the bigger machine, or they will need to develop a new methods and scenarios for this?
That's a very good question, and I think it depends on what we are talking about. This is certainly a hot topic, and this is the most interesting one, because if you can already create a hot pedestal emitter and keep the impurities already outside, you don't need to worry much. But probably this is going to work for some time, as you said, and if the post gets very long, gradually the impurities will make it to the top of the pedestal. And then I think the main strategy of ITER is going to be this strategy here, is to really apply localized heating in the plasma core, not with ion cyclotron, as I showed here, because this is what we are mainly doing for JET, but ITER, based on also results of other tokamaks, is going to apply electron cyclotron heating in the very plasma core to try to avoid the impurities to make it to the center. So you are right, relying on one technique only may be a bit dangerous. That's why I think that the more techniques we have, we can superpose to keep the impurities out of the plasma core, the better it is, and well, the safer it is for our operations in a future device. So having said that, the modeling of this part here, applying something in the very core to avoid the impurities, is very advanced. And people have been doing this and have been proving it's just a question of having enough power.
Okay, and the next question, please.
So I will ask a simpler question. Based on JET results, do you think the ITER scenario for DT fusion is already fixed? Or so how long is the way for ITER to still develop this scenario? Are we there yet, or we still need to spend years actually trying to fiddle and the shaping profiles and etc.?
That's a very good question, and I don't want to put my finger on this fire, to be honest, but I think you are right. From my experience, every machine reveals its own characteristics, and whether we like it or not, we will have to learn how to operate ITER in one way or another. Whether this will require substantial changes with what we do by now, I don't think so, but certainly it will require some learning and knowing what to do, how to, as you said, what is the best shape, where to put your strike points, how much gas you have to put in. That's engineering exercises, but ITER is foreseeing that. So there is a phase to study that and to get, well, acquainted with the characteristics of the machine. So I don't see a problem there. Actually, I see a very interesting future in that, because we'll probably learn much more about tokamaks at this stage.
Okay, I do not see any other hands up, so let's thank the speaker again. Thank you very much. So let's move to the second talk today, which will be given by Dr. Clement Trosseille from the National Ignition Facility. And we will learn more about the success of American research in the inertial fusion area. So please.
Thank you. All right. Hi, everyone. It's a great pleasure to be with you tonight. It's a great honor too, and it's also a great honor to represent a very large team of scientists, engineers, and technicians at the National Ignition Facility. People that have, worked on this challenge for a long time. Sometimes people that have dedicated their whole career working on this difficult problem of inertial confinement fusion, and so. What result am I talking about? Well, last year on December 5th, 2022, we produced 3.15 megajoule of fusion energy when we only used 2.05 megajoules of laser energy to confine and to fuse our deuterium-tritium capsule on NIF. So that's a gain of 1.5. And this is really the culmination of over a decade of experiments and learning at NIF. So on the, what's the other size? Should be good with laser, I suppose. Okay, so on the left-hand side here, I'm showing 10 years or 11 years of gain or fusion yield at the National Ignition Facility. And you can see that we started in 2011 very low. You can barely see the bars on the chart. But ultimately, after 11 years, 12 years, we reached this significant result, which had a worldwide attention for a good reason. So this result really is has required a concerted long-time effort to improve the target quality. You'll see that we use very small targets, capsules of deuterium-tritium fuel underneath. We also improved the laser accuracy, how we're able to deliver the laser power and control it precisely. The laser energy has been upgraded over the years. We've also improved the diagnostics capabilities, and all the learning that came with this 12 years of experimentation has helped us improve the design of the capsule, design of the whole room that contains the capsule, as well as the laser pulse. And I'm mostly going to talk about this December 5th result in this talk, but most of you know now that we did it again last July. We actually improved a little bit the performance of the fusion yield. 3.9 megajoule of fusion energy was generated in July, so that was a good confirmation that we were able to do that again. All right, so I'm going to first go back to the basics and tell you a little bit about fusion, what is ignition, and the National Ignition Facility. Then I'm going to tell you how we got there at the National Ignition Facility. And I'm going to end this talk by discussing a little bit the future with the inertial fusion energy, as well as the future plans for NIF. So this first slide, I think you guys have seen it like 50 times since we started yesterday. But I have to say it right. So what's fusion? It's the process that powers the sun and the stars. At the National Ignition Facility, we only use deuterium and tritium, which are isotopes of hydrogens, and we try to combine them with one another. And if we're able to achieve that, then the output of these fusion reactions is an alpha particle, a nucleus of helium, and a neutron. And the neutron carries most of the energy in these reactions, about 14 mega electron volts of fusion energy. So to give you a number, this energy released in this process for the same mass of fuel, it's of course why we're trying to control this process and harness the energy there. Yeah, I think that's yeah. So one thing I have to say is that, of course, it's not easy to fuse deuterium and tritium atom together with one another. We have to heat them to extremely high temperature so that we can overcome the Coulomb repulsion, because these are positively charged particles. And we also have to hold them very close to one another. We have to confine them so that they're in the vicinity and they have higher chances of fusing. So there are a few different concepts for combining a hot thermonuclear fusion plasma. The nature has found stars. And for example, the sun, our sun, is about 2 times 10 to the 30 kilograms of mass. So, 2,000 billion kilos. And all of this mass is very good at creating the gravitational pull that's going to prevent the charged particle from exiting the core of the sun. So that's how it works for the sun. Here on Earth, we have mostly 2 techniques. So I think with Dr. Lerche's presentation, you know everything you need about magnetic confinement fusion now, and the results achieved at JET and future plans for ITER. The National Ignition Facility, as I was discussing previously, uses this third technique, inertial confinement fusion. So what exactly is inertial confinement fusion? Well, it's a process in which we try to implode a capsule containing deuterium-tritium fuel by producing X-rays with lasers. And those X-rays are going to heat the outer surface of the capsule. And as it hits the capsule blows outward, is blown outward. And there is a rocket reaction effect that in turn compresses the capsule inwards. And at some point, the capsule has been accelerated and has been compressed so strongly that we create a hot central core, which we call the hotspot, which is surrounded by a dense plasma confining shell. And if we do things right, we initiate fusion reaction in the hotspot, which is going then to burn through the rest of the fuel and create conditions that are going to generate this fusion ignition. So to give you a little bit more details about how we do that on NIF, so the capsule that I was showing previously is placed in a horum. It's a cylindrical can, sort of oven, 10 millimeter high, and we have 192 laser beams on NIF, which are focused from the top and the bottom. And they enter the horum and they hit the horum wall and convert the visible the UV light of the laser to X-rays. Then the X-rays drive this capsule, as I was mentioning previously, and accelerate the fusion fuel to about 1.5 million kilometers per hour. At some points, we create this hotspot, which is going to have a density 100 times that of lead, as well as a temperature about 100 million degrees Celsius. That's about 10 times higher than the core of the sun. And if we do things just right, we initiate those first initial fusion reactions that are going to spread inside the dense fusion fuel. So the challenge really, and why it took us so long, is because it's very hard to do things right. We're trying to compress this capsule. It's a little bit like, if you're trying to compress a basketball to the size of a pea. You have to do that very evenly, and that's one of the key challenges. So NIF didn't happen in a day either. It's actually the result of many decades of work, scientific progress, initiated by John Nuckolls in the 1950s, which described a process for inertial confinement fusion originally. At the time, however, he didn't have a really good means to compress the fusion fuel. In 1960, the laser was invented, and with that, Nuckolls had this the tool he needed to efficiently compress the fusion fuel. And so in 1972, Nuckolls and co-authors, so Thiessen, Wood, and Zimmerman, published the seminal ICF, inertial confinement fusion paper. And since then, we've been building a series of even bigger laser facilities, starting from Janus in the mid-60s, 200 joules of laser energy, all the way to NIF, completed, and which started operation in 2010 with approximately 2 megajoules of laser energy. And again, as I was saying previously, it took us a while to get ignition. In 2020, we had the first burning plasma, where most of the power we got from the target was generated by alpha heating. On August 2021, we had the first shot that reached ignition by the Lawson criteria, although it's not it's one of the criteria that you can use to define ignition in ICF. It's not the National Academy of Science in the United States criterion, and so that's why at the time we were very excited, but we didn't have break-even, target gain of 1, which is the definition in the United States, which is what I'm talking about, this result that we achieved last year when we produced a gain of about 1.5. So I have also have to mention that the decision point to build NIF occurred in the mid-90s, and that coincides with the United States agreeing to stop any sort of underground nuclear testing for atomic weapons, which is something that a lot of other countries have agreed to and have been doing. And so we switched from a underground nuclear test to verify the performance, the safety, the reliability of the nuclear deterrent in the US, and we switched to a science-based stockpile stewardship program, which is enabled by NIF. One thing also I'd like to mention is that we're not only doing ICF experiment on NIF. There's a lot of other cool things that are happening, other high-profile experiments. There's a whole field of high-energy density physics that's being developed, that's been, pushed forward with NIF, research on laboratory astrophysics. There's been the discovery of superionic water in the core of the giant planets in the solar systems, for example. And it's also a great place to shoot movies. If you've seen the Star Trek movies, that was shot at NIF. All right. So this is a view of NIF, the world's most energetic laser. It's as big as 3 American football fields, tall as 10 stories high. And if you look, if you remove the ceiling, you can see the 2 laser bays containing each 96 laser beams on each side. The laser is supplied with 300 to 400 megajoule of electrical power that's stored in capacitor banks. And with all this power, we are generating about 3 megajoule of infrared light. So we're already lost, about 100 times what we used to create this laser light. And that's definitely something that you'll notice, and that I'm trying to show here, is that we are going to lose energy along the way, and some of it is by design. For example, the laser was designed in the 90s, and it's using 80s technology, so it's not very efficient. That's not the point of NIF. The point of NIF really is to try to show that you can get the target gain above 1, not the whole system gain above 1. So 3 megajoule of infrared laser light. Then we move to UV light, about 2 megajoule of UV light that enters the target here, the tiny target. I'm going to give you more details about it in just a second. Only 250 kilojoule of X-ray energy is absorbed by the capsule. And this capsule is about 2 millimeters in diameter, as I was mentioning previously. And so really, we are going from 300 megajoules of electrical energy down to only 20 kilojoule of internal energy absorbed by the DT fuel when we run an ICF experiment. So we're really sacrificing all this energy to achieve this energy density on the capsule with this big building and this tiny capsule. And what we achieve, losing all this energy, is the compression of the DT target, DT capsule, down to the diameter of something that's less than the human hair. So we've compressed the capsule by a factor of about 20, and by doing so, we've created the conditions that initiate the fusion reactions. So before I show you a nice movie of what an experiment looks like on NIF, just want to give you more details about the target, which are really, sort of work of arts almost, and that required state-of-the-art microfabrication precision, and are also cryogenically cooled to have the good properties. So this is the hull. It's a gold line uranium hull, 1 centimeter long. You can see the 2 silicon cooling arms here, as well as those wires that are connected to cooling sensors to monitor the temperature of the hull. You can also see here the outer jacket of the glass fill tube that's used to carry the deuterium tritium gas that is fed, that is transferred inside the capsule. The capsule itself is made of high-density carbon, diamond, And it's smooth to, the outer surface is smooth to 10 nanometer for 2 millimeter diameter. So if you scale that to the size of the Earth, it's as if the difference in elevation between the tallest mountain and the deepest ocean was only 60 meters. So it's extremely smooth. And on the right-hand side here, I have a radiograph of a capsule. And you can see the 3 different layers here. So the first one is this diamond carbon layer, about 80 microns thick. And the darker part here is still carbon, but it's been doped with tungsten. And we do that to prevent the X-rays from the horum to preheat the ice here, the DT ice here, which increases the stability of the implosion. The DT ice is formed by holding the capsule under high or cryogenically cooling the capsule for several days. And the capsule is filled with DT gas through this fill tube, which is about 2 to 5 microns thick. You can barely see it here. So that's, the fill tube is so small, and that's why it takes so much time to actually fill the capsule to the required pressure for our purposes. All right. So let's try to play a movie. There you go. So this is a NIF building. We're going to start in the NIF control room. So it's modeled after the control rooms that NASA uses in the space programs. We have many operators that control key components of the experiment. The laser as well as the diagnostics are precisely aligned as we go, as we prepare for the shot. Then the electrical energy is stored in these capacitor banks, as I was mentioning earlier, and then it's transferred to the main amplifier, where it is discharged through the flash lamps. The laser is born at the picojoule level, and is precisely shaped in type at the nanojoule level in the master oscillator room. That's this room here. And then it exits the master oscillator room, and it's going to be split 48 ways, so in 48 beams that are going to go to the main, to the preamplifier, where they're going to be amplified 10 billion times to the 10 joules level. Then they're going to exit the preamplifier, be split 4 more times for a total of 192 laser beams, and they're going to travel to the main amplifier. They're going to bounce 4 times in there, be amplified a further 10,000 times to and at this point, so each individual beam is a square of about 40 by 40 centimeter and has about 20 kilojoule of energy, each beam. Then the lasers are moving into the switch yard where they are redirected so that half of them enter the target chamber from the top hemisphere and the half of them to the bottom. And as they enter, the laser light is converted from red to UV with this harmonic crystal converter, and the beams are directed inside the horum from the top and the bottom through windows. And as I was mentioning previously, now you know everything about it, right? The lasers hit the horum wall, the light is converted to an X-ray radiation bath that's going to start compression on the fusion fuel. And if the conditions are aligned, the stars are aligned, I should say, then you can get fusion ignition. And we generate a lot of data, which is recorded by diagnostics, that is sent back to the control room and archived for further processing. And this all happens in sunny California. All right, so now let me go to the next part of the talk, which is how we got there. How did we get ignition on NIF? So if you think about it, what we're trying to do, igniting this plasma, we're trying to create a runaway process. Fusion ignition is a thermal instability where we start by initiating fusion reaction, which are producing alpha particles that are colliding with the surrounding DT fuel and transferring energy to that fuel. So it's heating it up, which increases the fusion reaction rates, which create more fusion reactions, more alpha particles, and so on. So we need to create those alpha particles, and those alpha particles need to heat the plasma and provide more power than the losses in the system. What kind of losses are we dealing with? Thermal conduction, although this type of loss is actually not too bad because most of the energy that we lose here is recycled in the surrounding DT fuel, and so it's actually heating that part of the fuel and contributing to creating the hotspot. Then we have X-ray radiation, Bremsstrahlung, that carries some amount of energy outside of the hotspot and cools the hotspot, so it's not good. And then after the capsule has reached the minimum size, the minimum volume, it starts to expand back up, and so we lose energy by mechanical work, this PDV work here. So we saw in the previous presentation that the Lawson criteria can be a way to measure how far or close we are to ignition, and so we do the same kind of things on NIF to measure, to monitor our progress towards ignition. We express it slightly differently here. It's the product of the pressure of the hotspot times the confinement times, tau, as a function of the temperature of the plasma. And so we have this boundary here where which discriminates whether the power from alpha heating dominates or whether the losses dominate. So we want to be on that side. And I'm going to show you what this ignition results, and as well as another shot where they sit in this sort of chart. So there's a lot of reasons why it took us so long to get there, and I can go into all the possible details, but one maybe obstacle I wanted to highlight is issue we've been having with hydrodynamic instabilities, which are very common in nature. I'm going to show you an example, but for ICF, they can really be disruptive. So the first type of instability is the Rayleigh-Taylor instability. It's when you're trying to push a fluid of high density with a lower density fluid. Here is an example here in a glass with these two fluids that are initially sitting on top of one another with small perturbation, and you can see how these perturbations have grown after a small amount of time. Another example found in the Crab Nebula here, where you can see those fingers that are symptomatic of this instability. And so, you can really start from a very smooth capsule, for example, and grow these perturbations many hundreds or thousands of times, and that's the main reason why we require the capsule to be so smooth, this 10 nanometer I quoted earlier. Another type of instability is a Richmeyer-Meshkov instability, which happens when you're trying to drive a shock through a two-fluid interface. And here is an example of how it's going to grow, and you can see those vortices that tend to appear after a little bit of time. It's not as bad as the Rayleigh-Taylor instability, but it generally can occur earlier during the implosion and create seeds that are then going to be amplified further by the Rayleigh-Taylor instability. So now I'm going to take you into a journey of about 800 experiments, DT experiments conducted over a decade on NIF, and that have seen an increase in target gain of about more than 1,000, and ultimately allowed us to reach fusion ignition. So we started in 2011, and at the time we had huge losses coming from laser plasma instabilities, as well as difficulty to have a good symmetry of the implosion. So laser plasma instabilities are typically occurring when we try to absorb the laser energy inside the horum, try to have the best coupling as possible, but these instabilities can cause backscattering, for example, or creation of hot electrons. These sort of things that prevent us from efficiently converting the laser light into X-rays. Then in 2013, we introduced the high foot design, which allowed us to better control the stability. But ultimately, we were still limited by the same instability sources because we were using horum of the same design. And so we achieved about 25 kilojoule of fusion energy by then, which is still a 10x, 10 times improvement over what we were able to do at the end of 2013. So this high foot design here is, you can see the laser pulse profile here as a function of time. And so that's really working on on the precise shaping of this foot to improve the stability of the implosion. Then in 2016, we switched to low gas fill Horam, as well as a new type of capsule ablator. We went from plastic to carbon, diamond. And it was a totally new regime, which we had to learn how to control. It took us a little bit of time. You can see the ups and downs there. But ultimately, in 2017, we achieved about 55 kilojoule of fusion energy, so new record. And then what we were trying to do in all this period was trying to, or at least early in this time period, trying to, let me remember, we were trying to improve the compression of the target, but we weren't really succeeding. We were always limited to compressions of about a factor of 20. So we had at some point an epiphany and tried a slightly different strategy, which was trying to rather improve the coupling of the energy to the target. And we wanted to do that by using slightly bigger capsules. However, we were limited with the fixed amount of power and energy, I should say, in the laser pulse, which prevented us from driving much bigger capsule because the implosion velocities were getting slower as we were driving bigger mass, which prevented us from effectively compressing the fuel and transferring the energy to the deuterium tritium fuel. So we tried to counterbalance that by using proportionally thinner capsule walls, but weren't quite successful. It's also at this time where we started to realize that the capsule quality had a huge impact because it could create mix where the ablator material was driven inside the DT fuel, which would spoil the probability of reactions, of course, a little bit like if you're adding sugar in your gas tank. So it was the beginning of a concerted effort to try to improve the capsule quality. Then in 2021, we used, in 2020, we used a slightly smaller capsule of much better quality, and we obtained about 170 kilojoules of laser energy, so that was a gain of 0.1 at the time. We started working on a set of parallel experiments to try to increase the coupling, and we ultimately achieved 0.7 target gain, so this August 2021 shot, which was for us already a huge success. And as I said, it was already meeting the Lawson criterion for ignition for ICF. But we didn't stop there, and we had a set of repeat experiments in 2021, 2022. We saw variabilities that led us to understanding a little bit more the causes of variability in this design and what we really needed to control. And ultimately, we obtained fusion ignition, this target gain of 1.5 in December 2022. All right, so this August 2021 shot I mentioned earlier produced 135 megajoule of fusion energy, and that places us is placed here on this Lawson metric space that I described earlier. So we're definitely, past the boundary for ignition. You can see all the other shots that we've done in the past that were definitely on the bad side of the line. And we did that by slightly reducing the laser entrance hole from 365 millimeter to 3.1, which was enough to reduce the losses in the system and push us past the ignition boundary. As I mentioned previously, this is a target gain of 0.7, so it doesn't meet the ignition criteria from the National Academy of Science, and it's not energy break-even either. So we kept going, we kept working. I want to say at this point that you might be wondering how we are able to actually place this shot here on this graph. Well, we have a lot of diagnostics, as I mentioned earlier. We apply about 3 dozens of diagnostics on every shot to try and measure, understand our improve our understanding of implosions. We're using the neutrons that are emitted by the fusion reactions as well as the other byproducts to monitor the conditions of the plasma, such as the temperature, the density, these sort of things. And it's something that's relatively hard to do because we're trying to measure something relatively extremely small and that's extremely fast. So we're basically developing the diagnostics on our own. We have teams that are dedicated to building those diagnostics. So I'm going to show you a few examples of those diagnostics. We have Dente, which is a low X-ray energy spectrometer that measures the whole-run temperature throughout the drive, which is important, because that's what we use to monitor how well we ablate the capsule material, how we drive the capsule. We also do X-ray imaging of the hotspot as well as spectroscopy, and with that we know the shape of the capsule in flight, as well as the electron temperature as the capsule reaches stagnation. We also do neutron images with pinhole cameras, and we do that in different line of sight to do tomographic reconstruction, and so that we have an idea of the shape of the hotspot as it's reaching peak compression. We measure the neutron yield, obviously. We have a nuclear activation detector that measure the decay of the activation of thin metal foil that are spread around the chamber. We also measure the X-ray bang time and the burn width, which allow us to know extremely well, for example, when the capsule reaches the peak compression compared to when we stop driving it with a laser, which we refer to as coast time. Burn width, which give us an idea of the confinement time, this tau parameter in this previous plot. We do the same with gamma rays using a Cherenkov cell detector, so that CO2 gas cells which are going to produce Cherenkov light, and it's going to be measured to do the same sort of measurement. And last but not least, we have a suite of neutron time of flight detector that allow us to measure time-integrated neutron spectrum generated by the fusion reactions that allow us to measure the temperature, the drift velocity, the compression of the target, the areal density of the target. And we do that along different line of sights. We have 5 different line of sights with a neutron time of flight detector. And so we can build these 3D maps showing the variation in the 3D space of all of these parameters. So overall, a DT shot, the diagnostics data as well as laser data generating on DT shot produces about 50 gigabytes of data. And we use our diagnostics to evaluate the degradation mechanism. So we have identified 3 main degradation mechanisms. The first one is the fact that as we try to implode the capsule, it doesn't necessarily stay in place. It tends to move one way or another to a few tens of kilometers per second to maybe 100 kilometers per second. So we lose efficiency in our process by transferring energy to the capsule to have a side motion rather than just imploding it spherically. And another source of degradation is the fact that we are not able to compress the target extremely uniformly. We have departure from spherical symmetry. You can see that in these neutron images here that are not precisely round, and that's another degradation mechanism. And the last degradation mechanism is the mix, the fact that, as I was mentioning earlier, we are injecting some part of the ablator capsule inside the DT fuel. And we measure that by doing some synthetic tomographic reconstruction of the hotspot from different line of sights with the images that we are generating, both X-ray images and neutron images, as well as using some spectroscopy data to constrain these reconstruction. And with all of that, we think we have identified the dominant source for the asymmetry and for the mix. So in terms of drift sources, we think it's mostly due to some non-uniformity in the thickness of the capsule wall. So when one side of the capsule is slightly larger than the other side. It can also be due to the laser delivery. excuse me, when there is an imbalance between one side and the other in the laser drive. And also these tiny hologram windows here that we have to let some of the X-ray escape for the X-ray diagnostics to actually be able to measure something can be the cause of some imbalance that we have to compensate for. In terms of asymmetry, the fact that we are departing from the spherical symmetry, again, it can be due to the laser delivery. We have different cones, angle of incidence that are entering the target, and there can be effects when one cone is not able to deliver all its energy to the hologram because of for example, some gold plasma bubble that is generated early in time that's going to block some laser from entering the hologram effectively later in time. And the last source, that we are attributing to a mix is the presence of high Z particulates on the surface of the capsule, as well as pits in the capsule. You can see here a photograph of the surface of the capsule, and you see those tiny holes here that are, nanometers or hundreds of nanometers inside that can be seeds for these instabilities that I mentioned earlier. So we think that we've been able to, overcome, or at least we're working for every single shot to overcome these instability sources or these degradation sources. And that's how we ultimately achieved the December 5th result last year, where we also benefited from an increase in laser energy. The laser energy was upgraded to 2.05 megajoule from 1.9 used on the August 2021 shot. And that allowed us to drive a slightly thicker capsule, about 6 micron thicker than in 2021. And we were able to use the increase in laser energy to drive the capsule for a little bit longer. So we were able to push on the capsule a little bit longer, which helped with compression. And that's ultimately how we got this result. And again, showing the loss on metric space here, the December shot is definitely past the boundary of ignition, the way we define it in ICF at least. So that's about it. That's about the journey, the path we took. And of course, we're not stopping there because we're getting a gain of 1.5. It's actually 1.8 or 1.9 now with the July result. But we want to go higher than that. And the reason for that is because of the plans that we are making, or at least, we are the hope that comes with inertial fusion energy for a new source of energy for civilian applications. So that's what I'm going to talk about now, and I'm also going to talk about the future plans for NIF. So what is, fusion energy first? We've talked about it already. It's this idea that we can get a source of energy that's going to be safe. In the case of inertial fusion, you're only really imploding a tiny bit of fuel every single time. And so there's no risk of runaway reaction, like what could happen in efficient power plants, for example. It's carbon-free, as you've seen, so it's good for climate change, obviously. Sustainable in the sense that there's a lot of deuterium fuel in seawater, as Dr. Lerche mentioned. Tritium, it's not as abundant, but the scheme that we're proposing is trying to recycle some of the neutron energy or some of the neutrons produced in the fusion reaction to create some more tritium by the breeding process. And I'm going to describe that later. So in theory, that should work. Other advantages, of course, compared to wind and solar, it's provide you the base load that you need to have energy whenever you need during the day, or if it's cloudy and there is no wind. It has, of course, huge strategic advantages for every nation to be able to be self-sufficient in its energy generation to meet its energy needs. And another advantage is, as Dr. Lerche mentioned, is that you don't have these fissile fission products that are going to, need to be stored for thousands of years. I think the half-life of the tritium is only 12 years, so it's not that bad. All right, so how would an inertial fusion power plant work exactly? Well, it would be pretty much the same as what NIF does these days. So you would still have a target at the center of a target chamber, and the target would be compressed on by a big laser. The real difference is that instead of doing that once a day, maybe you would need to do that about 10, 15 times per second. And instead of having a gain of 1.5, you would need to have a gain of about 100 to be able to produce a gigawatt of electricity with your fusion reactor. So 1 gigawatt is about what a fission power plant produces right now. But of course, if you're able to do that, well, you can use or create this reactor and create this power only using 5 tons of fuel per year. So that's much less than what you would require as coal. So okay, so that's the idea. Now, how do you do that? So you have to do that 10 times per second, as I said. So the idea is that the fusion neutrons are going to interact with the target chamber wall, which is going to be covered by a lithium blanket. And this has two reasons. The first one is that it's going to capture the neutrons and create heat. And this heat can be transferred to a boiler that's going to eventually, activate a turbine and create energy and feed energy to the grid the same way that we're doing on any other power plant, really. The other thing that this lithium blanket is going to do is that it's going to convert the neutrons into tritium, additional tritium that can be captured and reutilized to create new targets. And of course, you would have to do that online and be able to produce hundreds of thousands of targets a day, which is one of the huge challenges of this process. But that's really the basic idea. So as I was saying, we need to move from the single-shot operation of NIF to a 10 hertz operation for an IFE plant, which is challenging in many ways. We need to go to high gain, about 100 gain, rather than 1.5 that we have right now. The laser needs to operate with much higher efficiency. As I told you, the laser right now is only 1% efficient. We need to go to tens of percent at least, and it needs to be operated at high rep rate. Target production and cost, as I said, we need to implode targets a million times a day with this scheme. So we have to be able to produce them in en masse, and we need to be able to produce them for cheap, which is not easy. And then we need to work on the lifetime of the chamber and the optics, because it's going to be submitted to very harsh radiation condition, and all these neutron are going to be very harmful for the optics and all the other equipment. So next step for NIF, I think I need to wrap up here. 2023, well, that's almost done, or it's almost over, but what we wanted to do is prove that we're able to continue getting those megajoule or those igniting shots on a regular basis, or routine basis, and I think we've been relatively successful. We've had 5 megajoule plus shots since the beginning of the year, along with one fully igniting shot, the July shot. And we also want to improve the laser energy to 2.2 megajoule. It's actually going to happen pretty soon. I think it's tomorrow is the first shot where we've increased by another almost 10% the laser energy, which, as you've seen, is hugely beneficial to push us over the threshold of ignition. In the next 5 years, we have 2 main goals. The first one is to work on the long-term sustainment of the facility as it sees more neutrons. Some systems are aging, and we need to do an overhaul of many systems to allow them to continue to operate nominally in this very harsh environment. Also need to think about ways we can do to minimize the amount of time the personnel spend in the target chamber, because things gets activated and we need to figure out how to prevent people from getting massive doses if they were to come too often in the target chamber. And then the other step is also to continue increasing the laser energy to 2.6, maybe 3 megajoules. It's a little bit harder, but 2.6 is definitely feasible. And we hope to be able to get tens of megajoules of fusion yield by increasing the laser energy, as well as continuing refining our designs, obviously. And then in 10 plus years, the goal is to operate and obtain hundreds of megajoules again by leveraging all the learnings that we will be doing in the next 5 years. And of course, it's all very important for inertial fusion energy plans. It's also very relevant for the stockpile storage program at the National Ignition Facility. So that really two main drivers. So I think that's the end of my talk. I want to highlight again all the partners that we've been working with in the United States, but also in the rest of the world, both in academia and also a lot of industrial partners. And yeah, that's pretty much it. Thank you for your attention. Yeah, and we are hiring if you guys are interested.
Okay. So thank you very much. Congratulations for the results. And now it's time for the questions. Okay, please, first one.
Thank you very much for this very nice talk. I had a question about, well, it's a natural question, a bit about reproducibility. So suppose you now know how to do the pellet, you have your lasers in hand, and you would do this 10 times with the same pellet and the same laser. How many of these pulses will reach the Lawson criterion?
That's a good question. Yeah, and it's something that's definitely on our mind, and that's really also why we as I mentioned, right, we wanted to show that we were able to build a robust platform that's going to ignite every single time. So, there is variability. The targets, we can make the same target every single time, and some targets are going to be better than others. We characterize these targets. We have different means of characterizing, and we try to correlate the performance of an implosion with the number of defects we see in the capsules. I think we've proven that, and that's also why we haven't been able to try and reproduce this result many times in the past few months, because we actually have to cherry pick the targets that are going to have the best quality to give us the best chance of reproducing the results. But I think we've shown that when we do that, when we handpick the target, we are actually able to reproduce the results. So the targets are an issue, or at least a significant challenge. There are other sources of variability. So we have this program which aims at try to do some sort of machine learning process to try and really predict the performance of an implosion based on all the parameters that you can think of and that we can measure before the shot and try to come with some sort of probability of getting ignition on a given shot based on all these parameters. And right now, I think that these what we call cognitive simulations are able to give us a range of probabilities that is about a factor of a few one way or another. So it's not extremely precise right now, but that's what we're trying to build. Really, is this way of modeling the performance and give us confidence. Yeah.
Okay, thank you. Yes, here and next. You have already microphone.
Thank you for a very nice presentation. It was highly entertaining also. I have a question. So when you show these results, of course, you position targets very precisely, and this takes some time. And if you say you want to have 10, 15 heads, then of course they need to be flying in vessel. And how do you envisage actually aiming lasers at flying target? And do you plan these experiments also at NIF? I understand not with 10 Hz frequency, but any flying targets at NIF.
Yeah, so it's a good question. It takes a long time to align everything, the target, the laser beams that are going to interact with the target, etc. NIF itself can fire more than a few times a day. So at NIF, we are not trying to go at these high repetition rates. That's not the system cannot operate this way, and we are mostly relying on partnership with private companies, a lot of startup companies that have come up with designs based on this IFE concept and that have proposed ways of solving the issue with target alignment. An example that I've heard of, for example, is that you would have some sort of self-aiming lasers that would you would drop the target from the top of the chamber, and you would monitor the trajectory and correct for alignment live with some feedback loop that would slightly change the pointing of each laser beam to precisely implode every single target. So that's one way that's been thought about, but it's definitely one of the big challenges too for this concept. Yeah.
I have a simple question. So, how large fraction of the fuel is fused in your record shots? In other words, what is the theoretical limit of the gain that you can expect from the lasers that you have and the size of the capsule that you have?
Right. So I think, don't quote me on this, but I think if we were to burn all the fuel, we would be able to generate maybe 100 to 150 megajoule of fusion fuel, something like that. We're only generating almost 4 right now, so not a lot, right, is the answer, like a few % only. And that's why we're saying we can hope to get to much higher gains if we find a way to burn a bigger fraction of this fuel by implementing new designs.
Next question, please.
Just very technical one. You have, as far as I know, the lasers which are neodymium glass pumped by flash lamps. Mm-hmm. They are much more efficient ones produced now.
Yep.
Do you have any hope of overhaul of the lasers of the National Ignition Facility?
Yeah, so not really, because we can afford to waste, hundreds of megajoule of electrical energy, because we're not shooting the laser very, very long. And so if you're willing to just wait a little bit to charge your capacitor banks, then you're good. But of course, for the IFE concept, you would need to go from a laser efficiency that's right now at the percent level to something that is in the 20, 30, 40% level. And so, yes, using diode pumping and these sort of things instead of flash lamps would allow you to get much better energy. I think, again, this concept of IFE reactors, I've seen quote something like 20, 30% of laser efficiencies I think they can achieve with current technology.
I have also a question concerning the laser. Because I think you have chosen a long time ago the laser wavelengths with a constraint, because you want to use for optimized energy coupling some wavelength, but you have to use an existing laser system, so you have chosen the third harmonic. My question is, if you would be completely free to choose the best wavelength, what do you expect would be better than what you are using currently?
Okay. Well, so as you said, right, the coupling of the laser energy and how efficiently you convert to X-rays is tied to the wavelength. It's basically times to the force power of the wavelengths. So you want to go at the minimum possible wavelengths if you can, at least, to the first order. But then I think, there's going to be a limit to that. And so I'm not a very knowledgeable about what are the best trade-offs you can make. Generally, yes, you want to go to lower wavelengths. But at some point, you're going to be limited by, I don't know, maybe laser plasma instability or these sort of things that are not going to make it very worth your while to go into deep, smaller wavelengths. But I don't know exactly the answer to this question.
Also, I have a question.
Okay.
You said that one of next goal is to change the laser energy. What is needed to be done to change it, to increase it? What is challenging in this process?
Just need to dial it up to 11.
So why didn't you did it?
I'm kidding. So yeah. So I think that right now we believe that getting to 2.6 megajoule of energy is feasible with the current laser the way it is. The main concern we have is that as we increase the energy, the damage from the laser, from hotspots or backscattering or these sort of things, grows significantly, and it's sort of a trade-off between how much time we want to spend maintaining all the optics and the crystal and these sort of things, and the cost associated with that and the time versus the benefits that is anticipated in increasing the energy.
Okay, and how long does the process of ignition of whole shot? How long is it, and how often are you performing the experiment, the shots?
Yeah. So how long does it take to go from, let's start the shot to actually shooting it? It depends. It can be as fast as, say 8 to 10 hours. It can be as long as 40 hours if things go wrong. If you have a critical failure on some component and you need to actually replace it or whatever. So yeah, it varies. The second part of your question, well, as I said, right, we are not just trying to do ICF on NIF. We have a lot of other experiments. We have about 10 to 15 experiments per week, and maybe we're doing a DT shot every 2 weeks, best case scenario. And not always to try to get ignition. Sometimes it's to try to measure specific properties or measure a specific aspect of an implosion or a design that we think can help improve the performance. So we are really both limited by the availability of capsules, as I was saying previously, but also limited by all the other operational constraints that other users are using the facility, for example.
Thank you.
Okay, so last 2 questions, please.
Thank you. Well, maybe going a little bit out of the scope of your talk, I know that there are efforts in the United States as well, considering direct drive ICF. And I'd like to, if you could give a perspective from the point of view of the institution that you represent.
Well, so yeah, direct drive on NIF is possible. We have some experiments that use a direct drive and study the properties of implosion using this technique. It's not, the way that, it was not with this intent that NIF was designed, but. I saw your talk yesterday, and so you're very familiar with the experimentation that happens in Rochester in Omega, right? Where they do that. So I don't think that at LLNL there is any specific push to try and deepen our understanding or our experimentations associated with direct drive right now. We're really trying to push on the current indirect drive ICF and improve our designs, improve our understandings to get to these higher target gains.
Okay, and the last question, please.
Thank you very much for this very, very nice presentation. If I understand correctly, the whole realm is ablated. Yes? Then, going to the future, if you would have even 1 hertz, what happens to that material? It is not annihilated. Therefore, it will be deposited somewhere. Therefore, you will coat your chamber with gold, uranium, or whatever, but you will also coat your windows. How will you operate? And secondly, even for the laser light, how it will penetrate through this quite dense atmosphere.
So an excellent question. I think, yes, the whole RAM is mostly vaporized as after it's interacted with the lasers, which is going to create some residual, plasma, residual gas. I don't know. It's something that the IFE private companies are thinking about and are proposing designs. But I'm not sure on the top of my head what's the current thinking to achieve that, to overcome that challenge.
Okay, and I'm sorry, I have to also ask something. So does it mean that after you received your record, it means that you are able to perform the next experiment and plan that, for example, tomorrow, let's have an experiment where we have gain 1.1, for example. Is it possible? You are able and can repeat?
Well, so I mean, there is the scheduling aspect of things, as the facility schedule, both for DT ICF experiments and for every other type of experiment, is established a year in advance. So we have relatively limited flexibility to move things around and switch things around. We have some flexibility, but we are constrained by the facility configuration, for example, that has been determined in predetermined time. And then in terms of, reproducing things, repeating things, yeah, that's definitely something that we've been trying to do in the past. And I've shown you that between the August 2021 shot and the December 2022 shot, there was a long period of time where we weren't fully able to reproduce the results. And that leads to, this idea that we want to improve our understanding of some of the causes for the performance degradation and continue learning about these implosions. There's definitely a lot of room for, a better understanding of what exactly is going on and how we continue to make things better.
Okay, so thank you very much. Let's thank the speaker again. So thank you very much for your participation. I know that these 2 hours is probably not enough just to answer all your questions, but we hope that all the presentations brought you closer to our work and to fusion, to the results which community obtained. And let's hope that we will still hear about new records both in the magnetic confinement fusion and laser confinement fusion. So before I close the session, just information for press. So if there will be some special questions for our experts, I think we can stay and spend some time for this. So thank you very much for being with us, also for these who are watching us at the YouTube. So I close officially the session. Thank you. Maybe there will be some interest of the people.